Hello, my name is Hans Burgerhof and I work as a statistician in the UMCG. This video is part of a series of videos about medical statistics. In this video, I will give you some information about correlation, a way of expressing the strength of a relationship between two continuous or ordinal variables. Do individuals with higher weights have, on average, larger plasma volumes? Does age influence systolic blood pressure? Questions like these concerning the relationships between continuous variables are often seen in medical statistics. In previous videos, we saw how to compare groups regarding continuous, ordinal or categorical data, but how to test for relationships between two continuous variables. Like in almost all statistical problems, we will start with descriptive statistics. In this case, we will have a visual impression first, by making a scatter plot. I will use an example from the book of Kirkwood and Sterne, a small dataset containing information of 8 healthy males. 2 variables have been measured, the body weight and plasma volume. To see if there is a relation between the 2 variables, we will plot the plasma volume against the body weight. The first impression is that men with higher body weights have, on average, higher plasma volumes. But how to quantify the strength of the relation? How to test if a statistically significant linear relation exists? A possible way of expressing the relationship between two continuous variables is by calculating the covariance. The formula tells us something about the covariation of 2 variables. It's calculated by summing up the cross products of the deviations of both variables x and y and dividing by n-1. If we would calculate the covariance of the variable x with itself, so fill in x again for y, we see that the formula of the covariance leads to the variance of x. So in fact, the variance is a special case of the covariance. Now the covariance depends on the units of the variables. If we will calculate the covariance between height and weight, we will find another number if we measure in meters and kilograms than if we measure in centimeters and grams. To overcome this problem, we can standardize the formula of the covariance. We do so by dividing the covariance by the product of the standard deviations of x and the standard deviation of y. Because we use the same units in numerator and denominator, these units will cancel out. In the formula, also the n-1 cancels out. The formula on the right-hand side is known as Pearson's correlation coefficient. Usually we use the small letter r for it. Here we see the scatter plot of plasma volume and body weight again. The horizontal line shows the mean plasma volume. The vertical line, the mean body weight of the 8 healthy men. In this slide, I will try to explain the idea behind the formula of R, Pearson's correlation coefficient. If we look at this individual with relatively high body weight and relatively high plasma volume, we see a positive deviation of the x variable, meaning higher than average, and a positive deviation of the y variable. This individual will give a positive contribution to the numerator, because positive times positive is positive. For this second man, with relatively low body weight and relatively low plasma volume, we see a negative deviation of the x variable, meaning lower than average, and a negative deviation in the y variable. This individual will also give a positive contribution to the numerator, because negative times negative is positive. For man number 3 and man number 4, the contributions to the numerator are both negative, since negative times positive is negative. By summing up all these cross products, we can see if there is a positive or negative relationship between x and y. The denominator of r is used for standardization. Pearson's r is independent of the units used. You can show mathematically that Pearson's correlation coefficient is always between -1 and +1. If r equals 1, the points are on a straight line. There is a perfect positive linear relationship. Here you see an example of a perfect linear relationship. Please note that the correlation coefficient of 1 does not mean that the slope of the line equals 1. It just tells us that the points are on a straight line with a positive slope. If r is equal to -1, there is a perfect negative linear relationship. Again, r is a measure of linear relationship, and we use it for variables with a reasonably normal distribution. Here we see 4 scatter plots. In the left upper one, we see the variable y1 plotted against x1. Do we see a clear linear relationship? Does the value of x1 give us any idea about the value of y1? If we try to see the best fitting line through the data, it will be close to horizontal, with a lot of variation around that line. This indicates that a given value of x1 does not give us a clue about the possible value of y1, so hardly any relationship between y1 and x1. If we calculate Pearson's correlation coefficient in SPSS, the result will be 0.008, so very close to 0. If we look at the right upper scatter plot, we see a more clear pattern. Individuals with higher values on x1 seem to have, on average, higher values on y2. SPSS calculates a Pearson correlation coefficient of 0.81 for us. In the third graph, there is a negative trend, and the calculated r equals -0.808. What will be Pearson's correlation coefficient in the last scatter plot? There is a clear relation between x1 and y4, but Pearson's correlation coefficient is close to 0. Remember, Pearson's correlation coefficient is a measure of linear relationship. In the last example, the relation is quadratic. We know how to estimate the linear relationship. Now we would like to test the null hypothesis of no linear relation. So rho, the linear correlation in the total population, equals 0. If we have SPSS to calculate Pearson's correlation coefficients of these 5 variables, it will answer with a matrix of correlation coefficients of all possible pairs. In fact, we were only interested in the correlation coefficients in the first row. The estimated correlation between x1 and y1 was close to 0, and the p-value is given as 0.959, clearly larger than alpha of 0.05. So we will not reject the null hypothesis. There is no significant linear relationship between x1 and y1. The estimated correlation between x1 and y2 is 0.81, and the p-value is smaller than 0.05. So we conclude that a significant positive linear relation between these two variables exists. In the same way, we can see that there is a significant negative linear relation between x1 and y3 and no significant linear relation between x1 and y4. For the test on Pearson's correlation coefficient to be valid, we assume that both variables have a reasonably normal distribution. If this assumption is not fulfilled, we can use Spearman's rank order correlation coefficient. In fact, it uses the same formula as Pearson, but it's applied to the ranks of the observations instead of the observations themselves. To end this slide, a warning. Correlation does not imply direct causality. To give a silly example, in a study in Sweden, the number of storks was positively related to the number of deliveries in several areas. Now, I do not think that I will shock you by telling that there is no direct causal relationship. Possibly both variables are positively related to the fertility of the area. To calculate the correlation coefficient in SPSS, choose Analyze, Correlate and Bivariate. Here we see the SPSS output of Pearson's correlation coefficient between body weight and plasma volume. The coefficient is estimated as 0.759 and its p-value is smaller than 0.05. So we conclude that there is a significant positive linear relationship between the two variables. If we are not sure about the assumption of normality, we can calculate Spearman's coefficient. In this case, Spearman's correlation is also significant. So we can conclude from this analysis that a positive relationship exists. However, we are not sure about the linearity from this last test, because it's based on the ranks of the observations and not on the observations themselves. If we are interested in prediction, for example, we would like to estimate the plasma volume for a man with known body weight, we need a formula. In linear regression, we will estimate the equation of the best fitting line through the data. This line will look like plasma volume equals B0 plus B1 times body weight. I will tell you more about linear regression in another video. Now please make the exercises of video 10 and check your answers. See you in another video.